All right, here we are in chapter 9 where we started hypothesis tests. So just the basics here in this first section here. So you're either probably in the free response, so you'll either be doing a confidence interval or a hypothesis test. So a hypothesis test or a significant test is a formal procedure for comparing observed data with a claim, which are called your hypotheses, whose truth we want to assess. The claim is a statement about a parameter. We express the results of a significant test in terms of a probability that measures how well the data and the claim agree. So right now we're just going to talk about the underlying logic and how to perform tests about population proportion and population means. Basically what you're doing here is that you're trying to figure out if you took many samples and the claim were true, how likely is it that I'm going to get a result that I've observed. So a basketball claims to be an 80% free throw shooter. So you test it by having him make 53 throws. He makes 32, so you get 64%. So what can you conclude about that? So basically, I mean, there is a possibility that he got 64% just by chance alone, or maybe he was lying. So we need to kind of figure out what could happen if he really is an 80% free throw shooter. What possibilities are likely if we ask them this, because this is just his average, like it's not going to happen every single time. So they simulated this assuming that his average was 80%, and so these are the values that are likely for him to see if he really is on average about 80%. So if he shows you that he only gets 64%, that only happened 3 times out of these 400 sets here. So it is very unlikely that he would actually get 64% if he was really an 80% free throw shooter. So since it's so unlikely that we would observe that value, we are a little bit suspicious. So we would probably reject that he's an 80% free throw shooter. And again, this is just kind of stating what I've just was telling you. So maybe he just got 64% by bad luck, or maybe it's actually less than that. And then based on this, since it's not likely to happen, we believe that he probably is not really equal to 80%. All right, we always start off with we have a null hypothesis and the alternative. The null is the H0, H0. The null is the statement of no difference, so we always put the equal sign in that. The alternative is the HA, so that's the one we're trying to find evidence for. So in a free throw shooter, our hypotheses are the proportion was equal to 0.8 or the proportion was less than that. Your null will always be equal to, so it'll always be P is equal to some proportion, or mu is equal to some number. The alternative could be less than, greater than, or not equal to. Excuse me. And remember, there's never an equal sign in the alternative. So there's never going to be greater than or equal to or less than or equal to. The alternative is one-sided if it states that the parameter is larger or smaller than. So these first two right here are one-sided. They're only going in one direction. It's two-sided when it states that it's different, so it's going in both directions. They always refer back to the population, so never use p hat or x bar in your hypotheses. You're always using p or mu. Alright, so here's an example with assembly line workers. They have 18 subjects at random. Half of them are assigned to one group, half to the other group. They did similar work. One group was allowed to pace themselves. The other group moved at a fixed pace. After 2 weeks, they took a test on job satisfaction. So the response variable is the difference in the satisfaction scores. So we're going to look at the parameters, the mean difference, and job satisfaction scores. So all they were doing here is that they're just trying to figure out if job satisfaction differs. It doesn't give us a direction. So since it doesn't give us a direction, we're going to say not equal to, because we don't know if they think it's going to be less than or greater than. So we're just going to see if there is a difference. When we do a hypothesis test, our eventual goal is to get something called a p-value. So the p-value is the probability, assuming that the null is true, that the statistic would take a value as extreme or more extreme than the one actually observed. The smaller the p-value, the stronger the evidence against the null provided by the data. So when you have a small probability or small p-value, that's evidence against the null because it's not likely to get your sample result if the null is true. But large p-values don't give us enough evidence against the null because a large p-value says, well, it's pretty likely to get that sample result if the null is true. So in this case, back to the workers, the p-value is 0.2302. So the difference that they observed was 17 points. So what it means here for the p-value, so in this setting, what does the null hypothesis mean? So it just says that the difference would be, the null says the mean difference is equal to 0. So if it's true, then the workers don't favor one environment over the other on average. The interpretation of the p-value. Oops, this was supposed to not do that. The interpretation of the p-value is, so again, it's the probability of getting the observed sample result as extreme or more extreme in the direction of the alternative. So in this case, the alternative is going in both directions when the null is true. So what's happening here, so we would expect to see a difference of 17 or more points between the two environments. That would happen 23% of the time, because that was the p-value that they observed, just by chance if the null hypothesis was actually true. So then what they state here is they're just saying that, and the outcome would occur so often by chance. So 1 in 4, because that's like the 23%, and random samples of 18 workers when the null is true. So again, it's just saying, so the p-value is just saying what's the probability of getting your sample result. So there's a 23% chance of getting a mean difference of 17 points if the true difference were 0. Since it's such a high likelihood, so it's like 1 out of 4, we don't have any reason to believe that the null is not true, so we fail to reject. Alright, when we're talking about statistical significance, we're just kind of looking at that p-value. When we have a p-value that's small enough for us to make the conclusion to reject, then our results are statistically significant. Remember just that you're either rejecting or you're failing to rejecting. You're never going to say accept it or use language that you believe the null is true. We're never trying to prove the null hypothesis. We're trying to find evidence against it and for the alternative. So we're never going to say that we've proved the null hypothesis to be true. So to summarize, if your p-value is small, you're rejecting the null and you're concluding the alternative. If your p-value is large, you fail to reject, and you cannot. And then we got a little bit more specific. So we said, let's introduce something called a significance level. So that's going to be some fixed level. We used alpha that kind of gave us a cutoff or a tolerance level. So if our p-value was less than that, then we would reject and our result was statistically significant. So the summary here was if the p-value is less than alpha, reject the null and conclude the alternative in context. If the p-value is greater than or equal to alpha, fail to reject the null and conclude the alternative in context, or cannot conclude. So when I had you write your summary statements for that fourth step, I always had you compare the p-value to the significance level, state if you were rejecting or failing to reject, and then write that third statement in terms of the alternative. Can you conclude it or can you not conclude it? So here's an example about batteries. So they take a sample of 15 batteries. They are trying to see if the new batteries really last longer. So these are their hypotheses. We get this p-value. So what conclusion can you make at this level? So in this case, the p-value is less than alpha. So since the p-value is less than alpha, I can reject the null. And there is enough evidence to say that the mean lifetime of the batteries lasts longer than 30 hours on average. At the 0.01 level, I would say since the p-value is greater than alpha, we would fail to reject the null. And there's not enough evidence to conclude that the AAA batteries last longer than 30 hours on average. So again, compare your p-value to your alpha. Are you going to reject or fail to reject? And then make that last statement, should be a capital T, in terms of the alternative. All right, we also talked about errors. So you might be asked to describe or interpret the type 1, type 2 error, and then also describe the consequences of that. So there was this little chart here, and this is probably the best way to remember it, but your choices are either to reject or fail to reject the null, and then the other options are that the null is true or the null is false. So if you reject the null but it was actually true, you made a type 1 error. If you fail to reject the null and it's actually false, you made a type 2 error. Alright, so this example here about potato chips. So he's trying to figure out if more than 8% of the shipments have blemishes. If they do, then he's going to send the truck away. Otherwise, he's going to take the entire truck of potatoes to make potato chips. So he performs a significant test. So type 1 and type 2 error. So type 1 error is going to say that he's rejecting the null, but it's actually true. So if he rejects the null, he would conclude that the proportion of potatoes with blemishes is greater than 0.8, but the actual proportion is less. So he's making a type 1 error. He's concluding this proportion is greater, but is really not greater than, it's actually less than that. So if he concludes it's greater, he's going to send away the truckload, but he didn't really have to, so he lost revenue on those potatoes. The type 2 error, so he fails to reject, so he doesn't reject it. So he concludes that the proportion is actually still 0.08 or 8%, and he concludes, but it's actually not, it's really greater than. So he keeps the potatoes, he makes potato chips with this blemished potatoes, and then when he tries to sell them, people aren't happy with the quality. Alright, each type of error has a probability associated. The probability of a type 1 error is pretty easy. It's just the same thing as the probability of the significance level. The only way you're going to make a type 1 error is if you reject. The only way you're going to reject is if your p-value is less than that. So therefore the probability of type 1 error is the same thing as the significance level. Alright, the probability of a type 2 error is much more complicated, and it also is tied back to something called power. I didn't really cover this in class. What I've seen in the past on the AP exam is there may be a multiple choice question on power, but there's never been a free response question about power. So it's a complicated topic. It can take like a day to kind of understand it. So I kind of just skipped over it. Power is basically how good your test is. So if you get a multiple choice question based on power, you just do your best, just take a good guess on it. Some things you can kind of think about is like the sample size can impact. Like if you want a smaller significance level, you can take a larger sample. If you want higher power, you need a larger sample. So if there's a question that says something like, how can you increase your power? Just say, you could take a larger sample. So that's usually the big thing. And then here's the summary for this section.